Stress concentration charts look pretty complicated. There's a million lines on this drawing, but your TA Indiana's a pro. He'll help us out with it. And it's way better than actually using the equations themselves that these lines come from. So it's worth it to learn how to actually use these charts and save yourself a ton of calculator work. So first, to make sure you're in the right type of problem, your applied force needs to be a static load to use these charts. They don't work for loads that are dynamic or changing, like vibrations. Your material also has to be sort of a normal material, a regular metal. It can't be too brittle or too ductile, right? If it's really flexible, then you actually don't get stress concentrations near holes. Like the material will flex to adjust. And if it's too brittle, this concentration will actually just cause a huge crack immediately. And so, but just think a regular, normal steel, aluminum type stuff, that's going to be perfectly fine. All right, so while your TA Indy chews off the buttons on my shirt, the first thing is to make sure that you're using the variables that are on your chart. So in my drawing, the problem statement, lowercase d is the diameter of the hole. But you'll see on my chart here for the shoulder fillet, little d is actually the smaller dimension, right? Sort of this height. And so I'm changing my variables here. So on my horizontal axis, this ratio r over d is the radius of the fillet divided by this smaller height, this 1.25, not the diameter of a circle. There's going to be a separate chart for the hole later on. We're splitting this problem in two halves. First, we're going to find out what maximum load P can be applied that won't break at the fillet. Then we'll check what's the maximum load that won't break at the hole, and we'll compare those to each other to see which one would actually break first, which one is the more restrictive concentration. So we get R over D, 0.2, and then big D over little d, right? This is the 1.875 or 1.25 of about 1.5. So when I look up in the chart straight up from 0.2, find my 1.5 line, and then trace that back over to the left, I get a value of K of 1.82. This means that the maximum stress in my metal is going to be 1.82 times larger than the average stress that I would calculate just using regular force over area. And what's key when calculating area is you're using the smaller area, right? The fillet goes from a larger to a smaller. Use the smaller area. That's what these tables, that's what these charts have been designed for. So plugging in numbers, if the maximum stress that my bar can handle before it breaks is 21 KSI, when I divide by 1.82, that means I can't have more than an average stress of 11.54 KSI, because once you multiply 1.8, that could get up to 21. So now P divided by area, I can find then that I will reach this 11.54 KSI of stress with a force of 1.80 kip. All right, so let's switch to the hole. Hole's going to be a much easier version because, well, a hole is just a hole. There were a whole bunch more lines on the fillet curve because you had to account not just for the fillet, but also for the change in size as it went from larger down to smaller. So both of those factors changed, so you essentially had to account for two different things. But for a hole is just a hole. There's just the diameter of the hole. That's really the only value. So much easier to read chart. We go from, again, little d to big D. This time, actually, little d is the diameter for this chart. So we get a ratio of 0.4. Trace this up to the only line that's there. I get a ratio of 2.24 as my stress concentration factor, K. This still has the same meaning. K is the ratio of the maximum stress versus the average stress. And the maximum is the 21 that we're given. That's where the material will break. So dividing by 2.24, we get 9.4 KSI as the average stress that would result in breaking. When calculating then that stress is P over A, remember now we're using the minimum area. So the minimum area is going to be the area directly above and below the hole. So we're essentially taking the 1.875 height and subtracting the hole in the middle, the diameter of the hole, and just calculating like the area of those two rectangles up at the top and bottom. So we get a value of P of 1.32 kip, which we can compare to the P failure for the fillet of 1.80. A super common student mistake is to say like, well, 1.80 is greater than 1.32, therefore that's the maximum value for P. But remember, we're talking about the maximum value that will not cause it to break. If it's going to break at 1.32, then that's the one that will fail first. So that's the maximum value. And if I choose a value in the middle, like 1.5, right, that's clearly too high. That would already cause the hole to break. So 1.32 kip, the lower value of P, is the maximum value for P, as weird as that sounds. If you've been following along using the chart from your own textbook, you might have gotten a different value for the stress concentration factor K using the lines and curves in your book. Different textbooks have different tables and they don't all match up. So I prefer the ones that are in the Philpott textbook as opposed to the Hibbler textbook because they pretty closely mirror the equations that are in the Rourke's equations on stress and strain, or Rourke's formulas on stress and strain, which I think is kind of an authority on this subject. Your TA Indiana had to run off for some important kitty business, but he said that if this video helped you out, say thank you by leaving your favorite emoji down at the bottom, and he'll respond back with his favorite kitty emojis as a you're welcome.